Okay, welcome back. Today we're going to look at section 6.2, and this is on exponential models. So we're going to look at the growth and decay models using some word problems and then also some compound interest problems and the number E. So we'll talk about that coming up. All right, so we've already talked about the function f of x equals a to the x. So now we're going to add that extra number that we did in the last section. Sometimes they'll put another value in front of there. So now we're going to look at a times b to the x. So please remember that you can't multiply a times b together before you raise b to the power. Okay, so these numbers don't get multiplied. All right, so always b is going to be greater than 0. That's the number raised to the power, and it can't be 1. Okay, a can be whatever it wants to be, but b has to be greater than 0, and it cannot be 1. So we've already talked about the domain for every exponential function is all real numbers. So that's always true. A is what we call the initial value, which is going to be the y-intercept. Okay, that's always your initial value. And the base b is going to be either a growth or decay factor. Okay, so it's going to be a growth factor if the number is positive, and if the number is negative, then it's going to be a decay factor. Okay, so that's kind of how we're going to look at these today. All right, so let's look at a couple of these problems. Sometimes you're going to be given the equation to use, and sometimes you'll have to come up with that. Okay, so this example 1 says, if the rate of inflation, the growth rate of a certain item is 2.5% per year, the price P in dollars of the item can be modeled by the following exponential function, where T is the number of years from today. So P of T equals 2,000 times 1.025 T. All right, so you can see that this is the rate. So this is kind of a combination of the main price, 100%, plus this 0.025, which is 2.5%, and that's the yearly increase, okay? So together, you have 100% plus this 2.5%, okay? So that's going to give you the new price. So that's 102.5%, which we would write this way. All right, not that you have to have that right now, but just so you kind of know where that number comes from. So what is the current price of the item? So this A value, that's always the initial price. So currently this item is priced at $2,000. And then we're going to find the price of the item 10 years from today. So we would take this function and find P of 10. So substitute in 10 for the time. Okay, so 2,000, 1.025 to the 10th power. And it says round your answer to the nearest dollar. So please be careful when you're doing Hawks that you answer the question the way that it wants you to. So 2,000, you can put it in just like this, 1.025, and you're going to raise that to the 10th power. Okay, so exactly like it looks on your paper. So to the nearest dollar would be $2,560, since the 1 obviously is not 5 or bigger. Okay, so we end up with $2,560. All right, so that's just plugging in the numbers and working them out. All right, so now let's talk about compound interest. Okay, when you invest or borrow money with accounts that use compound interest, the interest is computed each compounding period on the principal amount of money invested or borrowed, any interest already accrued. Okay, so for these problems, you're going to need to know these words and the numbers that go with them. And in our formula in a minute, N is going to represent the number of compounding periods per year. So if it says your money is compounded annually, that means that's once a year. If interest is compounded semi-annually, that would be twice a year. If your money interest is compounded quarterly, that happens 4 times a year. Monthly would happen 12 times a year. Weekly, 52, and then daily, 365. So those are the values for your compounding periods for N. So let's look at the formula, and you need to know this formula. Okay, so for compounding, it's A equals P times, and then in parentheses, 1 plus the rate divided by the compounding periods, raised to the compounding periods times time. So use that value of n twice. P, remember, is your initial amount, or the principal. In banking, it's called the principal, but that's still the initial amount. And remember, you had that 1.025 before, so this is just going to give you the extra piece, for your interest. A is going to be the future amount, or the final amount that you have after so many years. Okay. R is your interest rate. Make sure you write it as a decimal. And then T has to be in years. Okay. For money, T always has to be in years. All right, then we already talked about N being one of these values up here. Okay. So you do need to know this formula. It's not going to be given to you. So we're going to do the same problem 3 ways. We're going to take $1,000 that's in an account that gets 3.5% interest per year. So as a decimal, that would be 0.035. Okay, you got to write that as a decimal. And then we're not going to take out any money or deposit any money. And we're going to figure out how much money we're going to have after 5 years if we compound our money annually, quarterly, and then monthly. So these are 3 different problems. So for annually, remember, n is going to be once a year. For quarterly, you would use n is 4. And for monthly, we're going to use n is 12. So based on the problem you get, you have to know which value of n you're going to use. Okay? All right, so let's look at the formula. So let's do this formula for annually. So we're going to use n is 1. We have our rate and we have our principal, which is 1,000. We're looking for A. How much are we going to have in there? So for this problem, we would do A equals the principal, which is $1,000, times 1 plus the rate, 0.035, divided by n, which is 1. And then we're going to raise it to the 1 times t power, n times t. So 1 times 5 years. Okay, so we can clean that up a little bit. 1,000 times, since this is just divided by 1, that's just 0.035 plus 1. So 1.035 to the 5th power. Okay, so we're going to put that in our calculator. So 1,000 times 1.035 raised to the 5th. And this didn't say what to give, so let's go out to the nearest penny. Okay, so that's usually how you write money. So this will be $1,187. And then we need to go out two decimal places, so we need to look at the third one. So since that's 6, that's going to become a 9. So that'll be 69 cents. Okay. All right, so we're going to do the same problem, but this time we're going to use quarterly. So we're going to put a 4 here and here instead of the 1s. Okay, everything else will remain the same. So A equals 1,000 times 1 plus 0.035 divided by 4 raised to the 4 times 5 power. Okay. All right. So when you do this in your calculator, you can put it in just like that. So we can do 1,000, parentheses, 1 plus 0.035 divided by 4, close your parentheses, okay, just like it says on the paper. And then we're going to raise that to the 4 times 5 power. So I'm just going to go ahead and write that as 20. Right? 4 times 5 is 20. So now we get $1,190.34, right? Since that's a 9. That'll become a 4. So 1,190.34. Okay. All right, so notice it went up a little bit because we got more interest, more times a year. All right, so lastly, we're going to do 12. So instead of the 4s, we're going to have 12. Okay, so 1,000, 1 plus 0.035 divided by 12 times a year, that's monthly, and then raised to the 12 times 5 power. Okay. All right, so again, we're going to put that in the calculator. 1,000 times 1 plus 0.035. This time we're going to divide it by 12. And we're going to raise it to, and you can write 12 times 5, or you can put in 60, okay? Either way. So we get $1,190 and this time 94 cents. So not a whole lot of difference. So just be careful in Hawks that you're putting in around it the way that the question asks you. Okay, and make sure you're just careful with your formula. All right. Next thing we're going to do is talk about the natural exponential function, which is f of x equals a e to the x. Okay, this is called natural exponential because we're using the value of e. Okay, remember e is a number. Okay, it's used a lot in banking because it's a growth factor. It's an irrational number, kind of like pi, and this is mathematically how we get that, but you need to know that it is approximately the number 2.718. Okay, so when you see e in a problem, it's not a variable, it's a number. Okay, so I'm going to talk about graphing that just so you can understand that. So remember, all exponential functions go through the point 0, 1. Okay, we did that in the last section. So remember, this would be like 2 to the x right here. So this is y equals 2 to the x. And then remember 3 to the x would be up here, right? Got a little steeper. So this one would be y equals 3 to the x, okay? Well, think about it. If e to the x is 2.718, that's somewhere between 2 to the x and 3 to the x. So e to the x is right in here, okay? So if you graphed it, that's what you would see. So it doesn't change any of the information because it's just a regular exponential function with a base that's bigger than 1, right? 2.718 is bigger than 1. So your y-intercept is still at 0, 1. The asymptote is still at 0. Oops. The domain is all real numbers, and the range still goes from 0 to infinity. So nothing changes. What you guys have to get used to is the fact that e is not a variable, okay? I also want to show you on your calculator, you've got 2 places to get e. You have it above the natural log button, which is the ln button right down here. You also have it above your division sign. The only difference is that this is just e, and then this gives you e and then an exponent ready to go. So if I wanted just to know e, then I would just do the division, the second divided by. So if I hit second divided by, I'll get e, and if I hit enter, you'll see that you get that number. If I hit second and the natural log button, look what happens. I'll get e, and then it gives me, get ready to put an exponent in. So if I was raising e to the second power or doing something with e, then I would choose this button. Okay, so it just depends on which one you need. So I'll just put a 1 in there, so I'll get the same value. Okay, so 2 places on your calculator, but just know that that's the number. Okay, that's probably the worst thing for these is that you forget that's the number. All right, so we're going to go back to the same problem that we just did in example 2. Okay, same exact problem, except now we're going to use this compounding interest continuous formula. A equals P times e to the RT. Most of you guys learned that and called it PERT along the way. But what we use this for is to compound our money when interest is compounded continuously. So if you look at example 4, it says, suppose you're still investing that $1,000 into an account, but this time it says it's compounding continuously. Okay? Well, if you get a banking problem that says that, you can't use this formula because there's no number for continuous. It's infinity, and so none of these would work. So you can't use this when your money's compounded continuously. If your money says it's compounded any other time, then you have to use this formula. So you can only use this PERT formula for when you see that word continuous, okay? But everything else is the same, 3.5% interest for 5 years. So we would use this formula, take $1,000, okay, using this formula, E is E. The rate is 0.035 times the time, which is 5 years. Okay. So now I would put this in my calculator, 1,000. So now I would want to use the second ln so that I go ahead and get the exponent. If you use just the regular e, then you can put in your own exponent. It doesn't really matter. And then 0.035 times 5. So we get $1,191.25 if we're going to round that up. And that would be our answer. Okay. So this is for compounding your money continuously. All right, look at example 5. How much money should be invested now at an annual rate of 7%, compounded continuously, to have $100 in 5 years? All right, so be careful with this. How much money should be invested now? So that means we're looking for P, and we want $100 in 5 years. So $100 is this amount. So P is going to be less than that, right? All right, so let me write that formula down. Okay, so we don't know P, that's what we're looking for, but we know that in 5 years we're going to have $100. And then we know the interest rate is 7%, and we know the time is 5 years. All right, so this time I'm just going to do e to this number. Remember, I can't multiply anyway, so I'm going to go ahead and do e to that exponent. Okay, so e raised to the 0.07 times 5. All right, so that gives me 100 equals 1.419. I'm going to go out to the 5, so 0.675 P, right? It's this times P. I just put the P at the end. Now, I don't want to round that in my calculator. Never ever round your numbers when you're working in Hawks. I'm rounding it on my paper, but I need to leave this and use this in my problem. All right, so what would I do now if I'm solving for P is I would divide both sides by this number. So I would take 100 divided by this number. Okay. That would give me P. So in your calculator, I'm going to do 100 divided by, and then I'm going to use my copy and paste. I'm going to go up here and hit enter so that I don't round it. And that'll give me my amount, $70.47. $70.47. That's how much I'd have to put in now in order to have $100 in 5 years. Okay, so just be very careful when you're using your calculator in Hawks, because if you round, that's going to change the cents. It might not change it a lot, but it'll change it enough to where Hawks will mark your problem wrong. So please do not round until the very end, okay? It's a big, big problem that you're going to get problems wrong if you do that. So don't round on your calculator. It's fine to round the numbers when you're writing them on your paper, but not doing the computations on your calculator, okay? All right, the last thing is to do other problems that are growth and decay that are not money problems, okay? So we're now going to look at this formula, this continuous exponential growth and decay. So I want you to notice that it is still PERT. It's just that we don't use a P for this amount because P stands for principal, and principal is usually money. So they changed the P to this A sub 0, but it's still the initial amount. So whether or not it's money for principal or other things, you know, animals or population or whatever you're doing, this is still going to be the initial amount, and then everything else remains the same, okay? So the only difference with this is that the time doesn't have to be in years. Remember from before, any money problem, you have to do the time out of years, but for other things going on in the world, you can use hours, you can use minutes, you can use whatever the time is in the problem, okay? All right, so let's look at example 6. So we have a species of iguanas is discovered on an island. The population of the iguanas is modeled by this equation. So 450e to the 0.12t, where time is measured. In this case, time is in years. What's the initial population of the iguanas on this island? So that, again, is always the original amount. So the initial population is 450. Okay. That's always easy to get the initial amount if you have the function. Find the population after 2 years. So we're going to substitute in 2. So we're going to find P of 2. So 450 e to the 0.12 times 2. Okay. So again, we're going to do 450 e raised to the 0.12 times 2. And it gives us 572, and we're rounding this to the nearest whole number. We don't want part of an iguana, so just 572. Okay. So after only 2 years, we're already up to 572 of these guys. All right, let's look at example 7. A patient receives 325 milligrams of a certain medication. The medication that is in the patient's bloodstream decreases, that's important, according to a continuous exponential decay model, and here's the rate. So since it's decreasing, the rate is going to be negative, and then change that to a decimal, so 26.264. Okay, so remember in this problem, if R is a positive number, that's growing, and if R is negative, then it's decaying. So it tells you in the problem it's decaying, so you need to know that the rate is negative. All right, determine the amount of medication in the patient's bloodstream after 12 hours. Okay, so we're going to take our function. All right, so let's see what we have. This is the starting amount, so that's a sub 0. Okay, the rate is negative 0.2. I like to put a 0 in front only because when there's a negative sign. So there's the rate, and then we're going to figure this out after 12 hours. So in this case, t is out in hours. So you don't have to change this to years or anything. Okay, whatever it is, that's what it's going to stay. All right, so this one is just straightforward. We're looking for how much is left. Now think about it. Since the rate is negative, our answer better be less than 325. Otherwise, we did something wrong. So 325 e to the negative 0.264 times 12. Okay, so that's what it looks like. So we end up with 13 point, rounding to the nearest hundredth. So it'll be 0.68 since the 8 is bigger than 5. Okay, so 13.68 milligrams. That's how much is left. Okay. All right, last problem. Assuming a current world population of 5 billion people at an annual growth rate of 1.4% per year and a worst case scenario of exponential growth, what will be the world's population in 11 years? All right, so again, take our formula. And again, if you guys want to write PERT, that's fine. You know, again, same thing, it's just a different letter there. So assuming that we're going to start with 5 billion, and we can just use 5, okay, we know that's 5 billion. And then we have the growth rate, so it's positive, so 0.014. And then the time, how many people will be here in 11 years? Okay. So we're going to do 5e raised to the 0.014 times 11. So we're going to go 2 decimal places, so 5.83 billion. So remember, these are in billions. Okay. All right, so that's how many people there would be in 11 years. All right, now, we've got a lot more to do with these kinds of word problems, but for now, you're just kind of learning the formulas and plugging in the numbers in the right place. So the one I want you to be careful of, because all the other ones, you know, we're finding the value, but don't forget, sometimes you're looking for the initial value and not the new amount, like we did in example 5. So just be careful with the wording when you see the problems, okay? All right, so you got problems to work on for homework. Let me know if you have any questions.